will not have human life sacrificed to experiment. Let this be the last day of the scientific age. Make this space come the symbol of all that drives us, and destroy it. Now! We don't want mankind to go up the moon and to the planets. We shall hate you more if you succeed than if you fail. We don't want you in the same world with us. Destroy the gun!
Channel 15, 14, 13, 12, 11, 10, retro, engines go, night go, count 3, go, entry, go,
Space is the place. Space is the place. Space is the place. Space is the place. From planet to planet, we travel the space. From planet to planet, we travel the space. Space is the place. Space is the place. Space is the place. Space is the place. Space is the place.
Hi, this is Gabe Ignetti.
And this is Isaac Arthur.
And this is the Ecomodernist Podcast.
Today we are about to reveal an amazing story. We are talking about our future in space. We are pleased to have with us as our co-host, Isaac Arthur. Isaac Arthur has a background in physics, but his real claim to fame is his science and futurism show on YouTube, which has a viewing audience in the hundreds of thousands. Isaac, why don't you introduce our guests?
Well, thanks, Gabe. I'll go ahead and introduce our next guest, Dr. Powell. He was a senior scientist at Brookhaven National Laboratory. His experiences have led significant advances in the design and analysis of advanced reactor systems, space nuclear thermal propulsion systems, electromagnetic hypervelocity guns, hydrogen and synthetic fuels, among other things. He holds patents for nuclear rocket propulsion and many other inventions, most notably the first and second generation maglev.
Well, Dr. Franklin Chang Diaz is a mechanical engineer, physicist, and a member of the NASA Hall of Fame. He holds a record for the most space flights, and he is presently the founder and current CEO of Ad Astra rocket company, where he's doing research and development on advanced plasma rockets. Gentlemen, welcome to the show.
Let's begin by asking both of you gentlemen about your work on advanced rocketry. Let's begin with Dr. Diaz.
Our project began more than 30 years ago at MIT, and then later it was transferred to NASA. So we spent about a decade developing the controlling physics of the engine at NASA, and then in 2005 we privatized it. And we've been the Ad Astra rocket company ever since, and we've continued to work on the technology maturation of the engine. We're getting ready for a major 100-hour full power test here in our facility in Houston. And that will be the last major test we do here on Earth before we start moving to space. That's where we are right now.
Okay. Dr. Diaz, you have come under a lot of criticism as to your work being impractical. What do you say to your critics?
Well, critics are good. It's always important for us to answer the mail, as they say. Sometimes the criticisms are valid, are important, and we have endeavored to answer these criticisms over the years. And that has helped us be more robust, to have a better design. But the engine is quite practical. It is the most powerful plasma engine in operation in the world today. It has a very good measured performance, over 10,000 individual firings. So it is not impractical, but it has been a very long process of technology development.
Dr. Powell, you've done quite a bit of work on atomic rocketry. Could you tell us more about it?
I started working on atomic rockets at Brookhaven National Laboratory in the early 80s. The problem with them was that they're very heavy and big. And so they would not be very useful for exploring the solar system, which is a real mission for atomic rockets because of their ability to get much higher thrust for a certain amount of propellant that goes through them. So I came up with the idea that if we put the fuel in the form of very small particles, you can get much more power out of a given volume. And so I talked to people at the Air Force Research Laboratory in California, and they thought it was a great idea. And then the Department of Defense got interested and became a classified program as part of its effort to defend against missiles, and became a real development program. For 5 years, we made a great deal of progress. Everything was working very well, and we're on track to have a ground test reactor followed by a flight test, and we would have achieved that, but the program stopped. But I kept working on it after I retired. I looked at it to explore and colonize the solar system and develop a second generation version of it, so to speak, which would be able to get much higher velocity and take much heavier loads to places like Mars or the Moon or Jupiter or beyond. And I think at this point where we're really starting to think about exploring and getting out and more into the solar system, I think it's a good technology. It's mainly just engineering development. There's no fundamental problems that would prevent it from coming into fruition. To put it in perspective, the engine would be only about the size of a garbage can. But the engine would be much smaller and lighter, and you'd get much more thrust out of the hydrogen than you would out of chemical fuels. You get 3 times as much thrust from a nuclear rocket per pound than you would from a chemical rocket. But the key is that you would not use the atomic rocket for liftoff from Earth.
Okay. Let me ask you this. Is the atomic rocket designed too dangerous for space launch from Earth?
Well, the atomic rocket would not be activated until they got up to orbit, and then they start out and then go to Mars or somewhere else. So if they're not activated, there's no radiation from them. Uranium is present all throughout the world, in the rocks and the sea and various other deposits. And we live with that kind of presence of uranium all the time. And so it's not a radioactive hazard. Once it's turned on in a reactor, yes, it produces fission products, cesium, strontium, other things. And those are radioactive hazards, but in space, it's not going to affect Earth. The rocket itself would be encased in a protective enclosure, and it would just come down to Earth, and that would be it. It wouldn't explode in a radioactive cloud. There'd be nothing of that. It would just stay as uranium with no fission products, no radioactivity. We already launch plutonium in rockets like the Cassini and so forth. The plutonium is radioactive, but it is encased in a protective enclosure in case of an accident, so it doesn't get out into the environment.
Let me ask you both, is there a place for both plasma and atomic rockets in a future space program?
Well, I don't see the chemical rocket as being capable of getting us much further than the moon. It is not very practical, but it is possible. It's possible to send packages to the outer solar system with chemical rockets. Atomic power is fundamental. There's no way that humans are going to populate the solar system without it.
I would agree.
Now you have a plasma rocket and an atomic rocket. Is it like apples and oranges comparing these two designs, or is one superior to the other and might beat out the other?
There is a place for both. You can think of the atomic rocket in the thermal mode, extremely powerful, a lot of muscle. And so you can think of that as a transmission operating in low gear, which allows you to climb mountains and lift very heavy loads. And then you can also think of the plasma engine as a transmission operating in a very high gear, which allows you to go to extremely high speeds. Maybe not without getting the initial push from a nuclear thermal rocket, but it gives you the capability to speed and shorten the trip time between points in space. So both of them have a place under the sun.
I wanted to point out that if we want to go to Mars, it's very important that we sort of minimize the trip time so that you protect the astronauts from cosmic radiation. And with the particle bed reactor, you could make the trip to Mars in about 90 days. With chemical rockets, probably it's going to take close to a year. So I think your astronauts will be much better shape when they land. And I agree with Dr. Diaz. There might even be a hybrid.
That was the original idea on the Bessemer, which was essentially a hybrid rocket engine, which would use the nuclear reactor in a thermal mode. And then as you sped to higher velocities and drive it in an electric mode, because our interest is shorter term commercial application, we've tabled that hybrid mode for a future endeavor, and we've concentrated on the purely electric application simply because of the realities of today. Nuclear space power is still not out there.
Dr. Powell, could you also tell us about your Strartram proposal for space launch propulsion?
Invented superconducting maglev, 1966. First generation design, now operating in Japan, reach speeds of 370 miles an hour. And they're building a 300-mile route between Tokyo and Osaka, which will carry 100,000 passengers per day. So it's a proven technology. So then 20 years later, started thinking about, well, why couldn't we use the same kind of system to launch things to space? Started looking at it and did a number of papers on it. The original idea was to run up a magnetically suspended tube up to about 20 miles where the atmospheric density was low enough. More recently, we've concentrated on launching it from a high altitude mountain and not with passengers because the deceleration forces would be too great.
What sort of game changer would that be?
Well, there's two game changers. One is that you launch enormous amounts of cargo up into orbit or trips to other planets and to the moon. The second application is to put up into geosynchronous orbit satellites that can beam down space solar power to Earth. The benefits would be astronomical because we would finally be able to transition away from fossil fuels. People don't realize that every year we burn 5 cubic miles of fossil fuels. If you put them on Manhattan Island, which is 22 square miles in area, the 1 year supply would be the Empire State Building. And by 2035, it would be up to Mount Everest. So we got to transition from fossil fuels. Solar panels in space can generate 4 times more power than they can on the Earth. And the cost would be less than conventional power costs. And the solar panels in space can generate 4 times more power than they can on the Earth. So it's tremendously environmentally attractive. The technology has already been demonstrated. They beam power from one Hawaiian island to another. I think it was about 100 miles or something like that. So we can do it. Just a question of getting the heavy weight of the solar panels up there cheap enough. You can't do it with a chemical rocket, it's too expensive.
How many people or tons of payload would something like Strartram be able to launch a year? And what would be like the cost per person or ton of cargo for that?
Well, as I say, if we're launching people from a high altitude mountain and it has to penetrate the upper atmosphere, the deceleration aerodynamic drag forces are too harsh. But for cargo, that's all right. And the cost to launch it's about $100 a kilogram. So that includes the amortized cost of the facility and the cost of the spacecraft itself. So one facility in Alaska could launch 100,000 tons a year.
100,000 tons a year. Wow. Some common concerns about Strartram and how you can build a tunnel that long and keep it evacuated there, the amount of energy you need to transmit to the ship down that tunnel, and how the ship handles that shock of exiting the vacuum into the air.
Those are good questions. First of all, the tunnel is not evacuated. It's a regular tunnel, but it has an evacuated launch tube inside it.
The best analogy I can think of is the CERN tunnel in Switzerland, the high energy accelerator, is 27 kilometers in circumference, but the tunnel is not evacuated. Inside it is a meter diameter tunnel, evacuated launch tube. And the people travel along the tunnel, servicing it, so forth, perfectly well. The CERN launch tube operates at 1 trillionth of an atmosphere with no difficulty at all. And in the U.S., we were about to build the superconducting super collider in Texas. It was going to be 87 kilometers in circumference.
Congress decided they didn't want to spend the money, so they stopped it, but it had already started. So long tunnels are not a problem. My favorite tunnel is the Goddard Tunnel in Switzerland. They just completed a railway tunnel. It's 50 kilometers long, and it works fine. It's almost as long as our Strartram tunnel, but it's bigger in diameter. It only costs $10 billion. So $10 billion is about what we're spending right now for a 2-mile across the Hudson River.
Getting a little deeper into that, when you just hit that atmosphere, it's been compared to jumping off a bridge and hitting into water at high velocity, and they say they could destroy the rocket.
Well, what we propose doing is sort of standard engineering, is what's called steam jet ejectors. You can position a series of steam jets around an entrance and push away the air, lowering its density to about 1/10 of what it is normally. So just as the rocket was being launched, you would have the steam jets create a sort of a partial vacuum around the entrance. But I like to point out that re-entry vehicles, the ones with nuclear warheads, don't have any problem coming down through the atmosphere. And they don't have higher densities. They survive.
They're going at very high speeds.
When re-entry vehicles come in, it's about 7 to 8 kilometers per second. That's about 18,000 miles an hour.
You say that there's just engineering problems in the way of building Strartram. Does that mean that if the government or governments decide to fund it, that there will be no problems whatsoever in bringing Strartram into fruition?
I don't think so. One of the things you always worry about is failure. If you launch something, it cracks open. You don't want it to fall on people. So we looked at sites that you would fly over the ocean, in Alaska down to Antarctica, so that once you launch, there's nobody downwind. You launch in a remote area, so there's no sonic booms. So I don't think there would be any problem if you choose your launch site well. And I don't think there's any safety problems associated with that. Basically, all the equipment is reusable except the craft you launch, and that's sort of basically a shell around the payload.
About how much we'll be looking for in terms of initial construction and annual maintenance and upkeep?
Initial construction is about $30 billion. That's based on existing tunneling costs, cost of the tube materials. Strartram is sort of unique in the sense that if you have a chemical rocket, you have 1, 2, or 3, maybe 4 or so engines on it. They all have to work perfectly, and they're very big and expensive. Strartram functions differently. It's using superconducting magnetic energy storage. So 1,000 modular loop units like it have been constructed on a somewhat smaller scale. So you got 1,000 little engines along the track. And so if one of them doesn't work, it doesn't matter.
And there would be no problem as far as generating that amount of electricity?
No, electric energy used in Strartram is about $1 per kilowatt.
How hard would it be to build a Strartram from the moon or Mars?
The physics would be easier because you don't have an atmosphere on the moon and a weaker gravity. So your requirements would be a lot more easier to fulfill. Now, the engineering of carrying on a construction project in the vacuum of the moon, that is still a pretty tall request. And we've learned a lot about building things up in space, but we haven't gotten quite to the point that we can build large facilities and structures there that work reliably. I don't see a major problem. It may be expensive.
If we do start building a lot of this stuff, we might start having problems with a lot of material in orbit. Could we talk about the space junk problem a little bit?
It's a real problem that we are now coming to realize more and more, especially in low Earth orbit. Certain orbits are more populated than others. And in low Earth orbit, there is a growing danger to our satellites and also our astronauts who are on the International Space Station. In every one of my flights, we worried a lot about getting hit by small particles. And every morning in the shuttle, we used to carry out a procedure of checking all the windows and taking pictures of all the little tiny little craters that specks of paint or washers or screws that are out flying at hyper velocities can cause on your spacecraft. So it is a problem, and we have to go clean up the place. Right now there's about 500,000 objects orbiting the Earth, and is liable to get much more populated soon because people are now going to these nano satellites that are being deployed all over the place.
I was just thinking, we were talking earlier about doing some solar power collection up in space. Those are very large objects that could get hit by debris pretty easily, so...
They're at geo orbit.
Yeah, these are problems that can be resolved. We have a proposal here to develop a orbital sweeper. It's a spacecraft that is able to go pick up those objects that are tumbling through space and can cause a great deal of damage, and also collisions with other satellites, create a lot of debris. So we want to pick up those pieces before they collide. These are big spent satellites that are still in one piece, but they have no control and they have no fuel, and somebody's got to go pick them up. Space sees no boundaries anymore. Basically, it is all one small spacecraft, which we call planet Earth, and we got to take care of it.
Could you speak to the shortage problem of plutonium for space travel?
There are two kinds of plutonium that we're really talking about. Lots of more kinds, but the two specific kinds are the plutonium in a nuclear reactor and Houston weapons. That's plutonium-239. The stuff that's used in space power systems like Curiosity rover is plutonium-238. We got lots of plutonium-239 in spent nuclear fuel, but we have almost nothing in terms of plutonium-238 for space power systems. Current inventories in the United States, it's on the order of 20 to 30 kilograms. And Curiosity rover took 5 kilograms, watts. And the reason that we have so little plutonium-238, it's just so inefficient and costly. One of the points that people don't realize is that, again, to make the plutonium-238, you've got to go back and reprocess fuel. We don't really do that anymore in this country. Reprocessing is a no-no now.
So you don't see much of a role for radiothermal isotope generators in the future except for small deep space probes, I take it?
I think the point is that we don't need plutonium, use uranium.
We'll go to regular reactors. There's lots more of it. It's a lot more power, and it's a lot more efficient. Plutonium thermoelectric generators are only about 5% cycle efficiency.
These little power sources of plutonium are just basically little hot rocks, and they don't turn off. And you just extract the heat and make electricity with that. There's very little. It's just enough to power these robots that go out into space, but it's not really suitable for propulsion systems or for humans.
Let's talk a little about the exciting developments of SpaceX. Elon Musk has set the goal of building a rocket so big as to send 100 people at a time into space. How difficult is the idea of mankind colonizing Mars?
Well, I really admire Elon Musk because he puts his money where his mouth is. I think that he has really pushed the rest of the community to think big, and I think that's great. Sending people to Mars, however, of course, is going to be not so easy. Mars is a place where it takes you the better part of a year to get there. Then you can't come back until Mars and the Earth line up again. That takes another year. And you're going to a planet that if there is very little air to breathe, so space is hard. Space is very difficult. So I'd rather we spend our efforts learning to live on another world, and we got one nearby, and we should use it. We ought to do our homework and learn first on the moon. There's a lot to learn, and in the end, we could end up at Mars a lot faster and a lot safer.
It's not just sending 100 humans to Mars. It's sending many, many tons of supplies and equipment and many, many more spacecraft carrying that stuff. And what I've proposed is basically landing a nuclear reactor in the north polar ice sheet of Mars, which is about 1 kilometer thick, and having it melt down its way and create things so you can minimize the trip time and maximize the carrying capacity. You can create living quarters under the ground. You can make fuel. You can grow things.
All this could be done remotely so that when astronauts colonize Mars, they can just walk into their nice rooms.
As long as you have power. Nuclear power is essentially life. And having a power-rich environment allows you to do all kinds of things.
I agree. I guess the one question I have, and I don't have any experience on it, but Dr. Diaz has, effect of lower gravity long-term on one's health.
Well, zero gravity is one thing. Low gravity is something else. So what appears to happen is that the body reacts to zero gravity. Basically gets rid of your bones. But in gravity of any kind, they're not as bad. And so the deterioration of human body could be a lot less just by having a little bit of gravity, as long as you have a very strong regimen of exercise and proper diet. I think it is possible.
I can imagine like people in their 80s and 90s who have trouble in our gravity well because of their age might love to go and live on Mars because they'd be young again. Their bodies would be so light. They'd be able to move around like young folks.
I'm 85, so I think I'd like it.
It's pretty tough. But certainly John Glenn did it. He was 77.
Dr. Powell, your maglev 2.0, that sounds like it might make that problem not really big at all.
Yeah, I think that's true. It could take 2G or a little less to accelerate to orbital speed. Even older people go on roller coasters at 2G.
Not me.
Obviously, a lot of folks want to know how would you keep it up that high above the mountain level, and, of course, what would happen if it fell down?
That's a good question. The whole thing is anchored with cables, both vertically and laterally. I looked up the wind forces, and from my analysis, the forces could be handled by cables. I wouldn't be certain of that. That's a very major question. That's one reason that we scaled back and concentrated on Strartram 1.0 just for cargo.
And Strartram had that same option where you can lower it if there's a hurricane coming in.
Yes, I think you could. Don't forget, the Strartram is kept levitated by magnetic force, so it could be done. I keep thinking, why are we explorers? What motivates us? When Sir Ernest Shackleton was pulling together his expedition to be the first to cross Antarctica, early 1900s, he sent out an advertisement in the London newspaper saying who would want to go on his expedition, and he couldn't promise anything except danger, possible death, and extreme discomfort. And he had 18,000 volunteers. So people want to do marvelous things.
Yeah, well, we'd like to thank you, gentlemen. It's been a tremendous pleasure and an honor to have you fellas on. And now for our final thoughts. We have heard the people say so many times that we need to solve our problems on Earth before we make any serious commitment to exploring and colonizing space. We've also heard that resource shortages will ultimately doom us to a complete collapse of our advanced civilization, perhaps even causing human extinction. It is well past time for us to move beyond our tribal wars and rivalries over our limited and dwindling resources and come together to boldly move forward to an age of infinite abundance and lasting peace. It's time to break out of our earthly straitjacket and reach for the stars. And that's it for our show today. This is Gabe Ignetti.
And this is Isaac Arthur.
We will be leaving you till next
20
time.
seconds and counting. Guidance internal. 15, 14, 13, 12, 11, 10. Retro. No. Engines go. Night. Go. Go. Count 3. Go. Entry. Go. Econ. Launch. Command. Go.
Space is the place. Space is the place. Space is the place. Space is the place.